Hey guys, and welcome to our second lesson here in chemical reactions. So we're kicking off a little bit of formula work today. Now this is not super interesting stuff, but it is going to lead us into some fun labs, so you're going to have to know how to do this stuff. First thing we're talking about is up until now, you spent most of your time talking about what we call molecular formulas. Now, there are actually two different types of chemical equations. Now, all of the stuff you've been seeing is a molecular formula because it's kind of the easiest to work with, the easiest to understand, and it represents all of the atoms in a molecule. So, for example, if I'm talking about sugar, C6H12O6. Fantastic. It's got 6 carbons, 12 hydrogens, 6 oxygens. I got sugar. But there's a second type of formula we haven't seen before. It's called the empirical formula. Now, the empirical formula represents the relative number of atoms in a compound. It's the ratio. So instead of writing sugar as C6H12O6, I can just say, well, it's carbon and hydrogen and oxygen in a 1 to 2 to 1 ratio. Or you could just say it's CH2O. So really all sugar is just a bunch of carbon, hydrogen, and oxygen, and I know that it is in a 1 to 2 to 1 ratio. So it just shows the ratio between atoms in a molecule. Now, obviously, it's not as useful. Like, you can't tell molar mass from this. It's not as easy to use chemically, but there's a very important reason for empirical formulas. I'll talk about that in a minute. I'll give you one more example here, a little simpler one. C2H6. Write it in proper notation. So if I give you C2H6 dicarbon hexahydride, and so what's the empirical formula? You're just looking at the bottom numbers. Say, okay, 2 and 6. What can I divide both those by? Well, 2 goes into them both. So we divide them both by 2. Carbon, 2 divided by 2 is 1. Hydrogen, 6 divided by 2 gives you 3. C1H3. Or you could just call it CH3. That would be the empirical formula. So why? Why would we ever want an empirical formula? Well, if you know the percent composition of each element, then you can find empirical formula. So let's say I gave you a chunk of some compound. Now, you don't know what it is. It's totally unknown. But you can manage to break it apart. Let's say you hook up electricity, you do electrolysis, and it breaks apart. And you can weigh what the different parts are. Or you use heat and break it apart into bits, and you can weigh the different parts. Well, if you know what the weights of the different parts are, it's pretty easy to find percent composition. And if you know the percent composition, you can get the empirical formula, and then you're well on your way to the handy molecular formula we all know. Like if I told you, like, hey, this is CH2O, that's the empirical. You know you're looking at either CH2O, C2H4O2, C3, you know what I mean? Like you can do multiples of it. And so it really narrows down what your compound could be. You could have a very good idea of what's going to be what here. So let's look at an example here. A compound has 40% carbon, 6.714% hydrogen, 53.29% oxygen. So we're going to look at C's and H's and O's again. Cool. What is our empirical formula for this? So here's step 1. Pretend that the chunk you got, the sample, was exactly 100 grams. Now, 100 grams is literally just a random number we picked because we are chemists and we are lazy, and the easiest possible number to work with percentages would be 100. If I have 100 grams, what's 40% of 100? Well, 40 out of 100 times 100 is just 40 grams. That's literally the reason we picked the 100. There's nothing magical about it. It just makes our math easy. So cool. Here's my 100 gram sample. If I know my percents, I got 40 grams of carbon, 6.714 grams of hydrogen, and 53.29 grams of oxygen. That's pretty straightforward. You take the percents, you just literally change the percent sign out for a gram symbol. And it's not magical math. We're just assuming we have 100 grams. If I could give you any amount, this system would work. But if we pick 100, it makes our math easy. So here's 100 grams. You put it into whatever you're going to do, the oven, electrolysis, it breaks down. You figure out what each component is. All right, I got 40 grams of carbon, 6.714 hydrogen, 53.29 oxygen. What do I do with these? Well, before I move on, you could probably guess, because all of these are in grams, and are grams really helpful for us in chemistry? Not so much, hey? So what are we going to turn it into? Well, we're going to turn it into moles. So step 2 is find the molar masses. Look it up on your periodic table. Carbon has a molar mass of 12, hydrogen's 1.01 roughly. Oxygen is basically 16. Now these have been rounded just to make them fit on the screen and look a little neater. Depending on how precise you want to be, you probably want to keep a few more decimal spots there. Now that I've got molar mass, if I have, I'll do a sample calculation for carbon here. I have 40.0 grams of carbon. I want to get it out of grams and change it into moles. And I know that 12.0 grams of carbon is a mole. 1 mole of carbon should weigh 12 grams. So I do 40 times 1. I divide it by 12. And I get 3.33 moles. I know it's not really fun to read math equations like this on the board. So that's why I wanted to show you the sample calculation here. This is what it would probably look like on your page to make it easier to read. Carbon. Start with 40 grams. Divide it by the molar mass, times 1, divide by 12. And that will give you how many moles you have. And you do this for each atom or each element in your compound. So I have 3.3 moles of carbon, 6.65 moles of hydrogen, 3.33 moles of oxygen. And you probably see where this is going now. The last step is to find the ratio. Well, without even looking at this, you could probably tell me if it's 3.33, 6.66, 3.33, it's probably 1 carbon, 2 hydrogens, 1 oxygen. The ratio is 1 to 2 to 1, right? But let's say those numbers were more confusing and harder to find. In order to actually solve it, what you do is you find which one of these is your smallest number. In our case, it's 3.33. You divide everything by that smallest number. 3.33 divided by 3.33 gives me 1. 6.65 divided by 3.33 gives me basically 2 after I round it. 3.33 gives me 1 again. And those numbers are your coefficients. Carbon, or subscript, sorry. Carbon, there's 1 atom. Hydrogen, there's 2. Oxygen, there's 1. So your empirical formula is CH2O. Which means if I need a molecular formula, it's going to be this. They're going to be multiples of each other, right? Or this. C3H6O3. I can just keep going up by 1, 2, 1 each time. Now I'll show you some tricks for that later on, but for now, CH2O. That's how you find an empirical formula. Let's give it a shot here. So we've got methyl acetate. It's 48.64% carbon, 8.16% hydrogen, 43.20% oxygen. Step 1, what do we got to do? Well, we got to pretend you got 100 grams and figure out how many grams of each you'd have. So I'd have 48.64 grams of carbon, 8.16 grams of hydrogen, 43.20 grams of oxygen. All right. Step 2 and 3, I kind of put them together here. You find the molar masses. Carbon is 12. Hydrogen 1.01, oxygen 16. You divide the mass you had by the molar mass. And so it turns out I've got 4.05 moles of carbon, 8.10 moles of hydrogen, 2.7 moles of oxygen. So I kind of put step 2 and 3 together here because it's just pretty much one step, really. You're calculating number of moles. You just so happen to have to find molar mass as part of that equation. So we've got our number of moles. Now what do we do with that? We'd have to go to step 3. We'd have to divide them, right? So which one's the smallest here? Take a look at my number of moles section. And it looks to me like 2.7 is my smallest. So if I do 4.05 divided by 2.7, that'll tell me carbon's ratio. Wait a second. That gives me 1.5. 8.10 divided by 2.7. So suddenly you got decimals. What? So it's a 1.5 to 3 to 1. You're not allowed to have decimals. You can't have 1.5 carbons for every hydrogen. If I'm looking at empirical formula, it's telling me how many atoms there are. I can't have 1.5 atoms. You can't have a half an atom. That doesn't make any sense. You can't break atoms apart, right? If you're looking back to our, well, you can, but it's really hard. It's not going to split in half. So not allowed half atoms. So what do you do when you end up with a decimal You double everything. It's similar to when we're balancing, right? If you're balancing and something's just not working out, how do you get rid of it when you're stuck with it? I change one and the other changes. Change one. Whenever you get stuck on balancing, you double it. Whenever you have a decimal here, you double it. Multiply it by 2. So our carbon goes from 1.5 to 3. Our hydrogen goes from 3 to 6. Our oxygen goes from 1 to 2. And so our empirical formula becomes carbon 3, hydrogen 6, oxygen 2. So you follow the exact same steps, but if you get to a decimal, you might have to double it. Worst case scenario, you have like a 1.25 or something. You might have to double it twice, but you should be able to double until you get rid of it pretty easily. If you double it once or twice and you're not getting rid of it, there's a good chance there was an error somewhere in your molar mass or otherwise. And so that's pretty much it for empirical formulas. Like, that's all you really got to do to solve them. So I'm gonna give you guys a little chance, a little time now to just work on those, practice it, and get really good at it. So that's it for empirical formulas, and I'll see you next time when we talk molecular formulas.